Hey guys, I'm gonna just go over this 6.7, 6.9. This is that kind of second half of the homework. This is just focusing on antiderivatives. Some of them are definite, some of them are indefinite. So yeah, I think the second part, the second page of these right here is using U substitution. These ones are just using basic derivative or basic anti-derivative rules. So for this first one right here, we have 2 minus 1 over x. So the antiderivative of 2 would be 2x, and the antiderivative of 1 over x is going to be the natural log of x. Don't try and use the power rule here, or don't try and write that as x to the negative 1 and use the power rule. It's not going to go well. And then we're evaluating this from 1/2 to 3. So we'll do f of b, and then we'll subtract f of a. So first plug in 3. So if I plug in 3, I'm going to get 6 minus the natural log of 3, and then minus, and then we'll plug in 1/2. If I plug in 1/2, that will be 1 minus the natural log of 1/2. Now, as far as simplifying goes, there's not a whole lot yet that you really need to or should have to do, but I will, for the sake of just, because I can't not, gotta combine constants, right? So 6 minus 1, that's going to be equal to 5, and then minus the natural log of 3 minus the natural log of 1/2, and I would really like to simplify this right here, but I think you guys would freak out. So I'll leave it, but it just bothers me, but whatever. So also, as you go, I think you guys should be checking your work. And so if you don't have a calculator, go to Desmos, and you can check integrals in Desmos. So just make sure that whenever you have the line, you're going to type in int for integral, and you can see that the notation and everything comes up for you. And so we're evaluating from 0.5, so 0.5 to 3, and it's 2 minus 1 divided by x. Don't forget that you do, after all this, you need to put in dx. Right? Maybe I put parentheses around this whole part right here. Yeah, there we go. Okay, so put parentheses around the 2 and the minus 1x. That's called the integrand, by the way. I'm not sure if we've talked about that in class, but so I get 3.208. So let's check it in our calculator. Let's do, we said 5 minus the natural log of 3, and then minus the natural log of 1/2. Oh, this is embarrassing. 5 minus the natural log of 3 minus the natural log of that should be plus right there. That one's for all you guys that were complaining today about all my mistakes. I catch them eventually, most of the time. Okay, enter 3.208, and yeah, that's what we had in Desmos, right? Yeah, 3.208. Okay. This one here, antiderivative for x squared is going to be 1 over 3 x to the third. And then the antiderivative of square root of x, I'm not sure if you guys have memorized this one at this point. It might be worth memorizing because it's probably going to happen a lot. But it's going to be x to the, we have to add 1, which would then become 3/2, but then we'd have to divide by 3/2, which would be the same thing as multiplying by the reciprocal. And so that's what the antiderivative there is going to be. So plus 2/3 x to the 3/2 from 0 to 1. And we can plug in 1. Here's the good thing. This is really easy to evaluate. By plugging in 1, this is just going to become 1/3. That's going to become 2/3. So 1 plus 2/3. And then if I plug in 0 for both of those, it's just going to be 0 plus 0. So, 1/3. I'm just going to start making purposeful mistakes just to bother you guys. So 1/3 plus 2/3, that's just going to be equal to 3/3, which is going to be equal to 1. And let's go ahead and check that. So integral from, I think it was from 0 to 1, and then we're going to have x squared plus the square root of x and dx, and we got to put parentheses around the integrand apparently, and it's equal to 1. Okay, let's see here. You know what I'm doing a bad job of is making sure the antiderivative's derivative is that right there. But hopefully you guys are doing that. Alright, so, or not, I don't know. X to the negative 6/5, so this is just going to use the power rule. So that's going to be x, we're going to add 1 to that, and that's going to make that negative 1/5. And then we're going to divide by negative 1/5, which would be the same thing as multiplying by negative 5. And so times by negative 5, integrate from 1 to 32. Right now, I'll double check this. So if I bring this down, if I take the derivative of this, the negative 1/5 times by the negative 5 will cancel, leaving me with x. And then if I decrease the power by 1, yeah, I get that. Okay, and then let's see. So let's evaluate. So we got negative 5. I'm going to plug in 32. 32 to the negative 1/5. And then minus 1 to the negative 1/5. And this right here will be 1/2. So that's going to be equal to negative 5, because that's the same thing as 1 over 32 to the 1/5, which is equal to 1 over 2, since the 5th root of 32 is 2. Okay, so it's going to be 1/2, and then that's going to be minus 1. So negative 5 times by negative 1/2, so that comes out to be 5/2, yeah? And just do a quick check. We're going to do, what was it? X raised to the negative 6/5, right? Close that parenthesis. Undefined. 6/5, 1. I need to change my bounds. There we go. 1 to 32, and we get 2.5. Cool. Got a trig derivative, or trig antiderivative here. So the antiderivative of cosine, is that going to be negative cosine? Because the derivative of cosine is negative sine of x, and then times by the negative that we have right here, which would turn positive. So yeah, negative cosine of x from 0 to pi. So we'll do negative cosine of pi minus cosine of 0. And that's going to turn to be negative cosine of pi is negative 1. So negative 1 cosine of 0 is 1 minus 1. So that's going to be negative 2, which will be 2. So let's check that here. We're going to do this to pi. Change this lower bound to be 0. Change the function here to be sine of x, and we get 2. Cool. Alright. So for 5, another trig. Got a couple. Oh, got a lot of trigs here. I think I did that because of you guys. So let's see. Secant squared of x. The antiderivative of secant squared is tangent. So 2 tangent of x, and from 0 to pi thirds. let's see here. So 2 tangent of x and pi thirds. So 2, right? One second, let me check my antiderivative. Derivative of tangent is secant squared. Yeah. So we'll get 2, and we'll do tangent of pi thirds minus tangent of 0. Pi thirds, that's a 60-degree angle. So 60 degrees. We would have 1, 2, and root 3. And then tangent is opposite over adjacent. So this would be equal to 2 root 3. And I'm pretty sure tangent of 0 is 0. And so this should just be 2 root 3. Let me check what 2 root 3 equals. So 2 root 3, 3.464. And let's test that out here. So 2 secant of x, I'm going to have to square this right here. Squared, and change that to be pi thirds, and we got 3.464. Alright, the antiderivative of secant x tangent x is secant of x, so the integral from 0 to pi just 4 secant of x from 0 to pi thirds. And then plug in pi thirds, so secant of pi thirds minus secant of 0. Okay, well, a good thing I have pi thirds here. Secant is adjacent over hypotenuse, because that's the reciprocal of cosine, right? So that's going to be 4, and then we'd have 1/2 minus, and secant of 0, secant is 1 over cosine. Cosine of 0 is 1, so that's just going to be 1, right? So secant of 0 is 1. So this becomes 4. And then we would have negative 1/2, so that becomes negative 2. So we would have 4, and we're just doing so 4 secant tangent. 4 secant, I don't want that there. And tangent of x. Oh my gosh, this is embarrassing. 4 secant x tangent of x from 0 to pi thirds. Why is it 4? Let's see. Antiderivative. The derivative of secant of x is secant x tangent x times by 4, integrating from pi thirds to 0. 4 secant of pi thirds is, oh wait a minute, it's 2, not 1/2. Cosine of pi thirds is 1/2. Secant is 2. I wish I could say that was on purpose, but it wasn't. And that's going to be equal to 4 times by 1, which is going to be equal to 4. There we go. All right. I'm a good example of checking, of helping you guys remember that it's always important to check your work, no matter how good you are, or how bad you are, apparently. Let's see. Antiderivatives of cosine, that's going to be equal to sine of x. And the antiderivative of 3x squared, that should be x to the third. And since this is an indefinite integral, we're going to add c. So the derivative of sine is cosine. Derivative of x to the third is 3x squared. Yep, checks out. This one right here, so the antiderivative of 2e to the x is 2 e to the x. Antiderivative of secant x tangent x is secant of x. And the antiderivative of square root of x, we did that all the way up here. So 2/3 x to the 3/2 and plus c. Plus c. Okay, and I think that checks out. Whoops. Okay, on this next page, it's going to be substitution, and I'm going to be honest, I know how to do this one. I'm not saying I don't know how to do this one, but I don't want to explain how to do that one. If you guys want to try it, it would be better if you wrote this as sine of 4x plus 2 over cosine of 4x plus 2. And you can try and make either this u or this u, but also keep in mind that you might need a second layer of u substitution because of the inside part right there, unless you know how to, never mind, don't want to get into it. But yeah, if you want to give that a go ahead and have fun with that one, but I don't want to do it. For 10, so when I'm using a u sub, when I'm practicing u sub, I look for, remember that oftentimes there can be a product because, so the derivative of x squared plus 1 is x. So maybe the fact that I'm multiplying by x on the numerator is a result from the chain rule. That's what I'm trying to say. And so that's where we usually like to use this u substitution technique, is whenever it's possible that we see that this is the product of a chain rule. And so if I allow u to be equal to x squared plus 1 du, sorry, this is for A4. I need to apparently work on my u's. Du dx is equal to x squared plus 1. And then that would mean that dx is equal to du over x squared plus 1. What the flip? No. 2x. Sorry, I got so caught up in writing my u's the correct way. Let's see, so du over dx is equal to 2x, and dx is going to be equal to du over 2x. Okay, so let's make our substitution. So we got the integral of x over u times by du over 2x. And we can cancel that part out, which is nice because now we're strictly in terms of u. So we have the integral of, I'm going to put the 1/2 out here, the 1/2 coming from that constant in the denominator there, of 1 over u du. And the antiderivative of 1 over u is the natural log. So that's going to be 1/2 times by the natural log of u plus c. And we can undo our substitution. So u is x squared plus 1. So 1/2 natural log of x squared plus 1 plus c. And again, good thing is that it's always easy to check your work because derivatives are easier, right? So if I have this constant here, the derivative of the natural log, so this would be 1/2 times by 1 over x squared plus 1. And then the chain rule, multiply by the derivative of the inside, that's going to be 2x. But you can see that the 2's would cancel, leaving me with x over x squared plus 1. And that does match what I have right there. Okay. Let's see here. This one is a really easy u sub. The thing is, there's no product, but you can tell right here that it's x plus 1. That's really easy, and I know what the derivative of the square root is. But here's the thing, because the derivative of the inside is 1, I'm honestly not going to go through the troubles of using this whole process of u substitution, because I don't have to eliminate, I don't, like in this one right here, I don't have to eliminate x. So putting in u, I'm going to get du is equal to dx, essentially. So I don't have to eliminate another part. There's no other part to eliminate. So I'm just going to treat this like the integral from 0 to 3 of the square root of u du. And I can just go ahead and take the antiderivative, which we've been doing a lot. The antiderivative of the square root of u would be 2/3 x to the, u to the 3/2 power plus c. And then I can say 2/3 x plus 1 to the 3/2 power. Yeah, but also this is not plus c because we have, this is a definite integral. So let me backtrack. See, I don't want to use u. This can just be this is just going to be 2/3 I'm so conflicted right now on what I want to do here. Yeah, I'm gonna skip the u sub part. I don't care. Square root of x plus 1, and not the square root, x plus 1 to the 3/2 power from 0 to 3. Okay, so I'm skipping through all the u sub part because, like I said before, it's just, I'm not trying to cancel anything out, and the derivative of the inside is going to be 1. So it's just going to be a lot of work for something that I know how to do without using the u sub. And I can check my work here. So if I drop down the 3/2, that's going to cancel with that right there. And then I'm going to decrease the power by 1, giving me the square root of x plus 1, which is indeed what I have right here. So again, just bypass all that because I'm not trying to cancel anything out. And then let's go ahead and evaluate this. So that's going to be 2/3. If I plug in 3, that's going to be 4 to the 3/2 power minus, and I'll plug in 0, that's going to be equal to 1 to the 3/2 power if I plug in 0 right there. And then that's going to be equal to 2/3. I'm going to do the square root of 4, which is 2, and then cube that, which would be 8, and then minus 1. So this is going to come out to be 14/3. So let's check this here. We got the square root of x plus 1, and the upper bound is, what was the upper bound? It was 3, and 4/16 is 14/3, that. 2/3, yeah, 4 2/3. All right. Moving on here, now I see that I do have two parts. There is a product. I'm probably going to use the u substitution method here, and I'm also probably going to replace my boundaries. So which of these, if I take the derivative of, equals the other? I know the derivative of tangent of x is secant squared. So I'm going to allow u to be equal to tangent of x, and that would mean that du dx is equal to secant squared of x, and then that would mean that dx is equal to du divided by secant squared of x. So now also, as far as replacing my bounds, because I have this function of u here, so we'll do the integral from, if I plug in pi fourths, negative pi fourths, so let me quickly, pi fourths, that's a 45 45. Wow, drew an arrow. What the heck? Cool. 1, -1, and square root of 2. So tangent is opposite over adjacent. So if I plug, wait, why did I do that? Oh, so I'm plugging in -π4, and tangent of -π4 would be -1. And then if I plug in 0, tangent of 0 is 0. So -1 to 0. Now these are in terms of u, not x. And then I have u, secant squared of x, and then du over secant squared of x. So those will cancel, those will cancel. Integral from -1 to 0 of u du. And the antiderivative of u would be 1/2 u squared. And from -1 to 0, so it's going to be 1/2 0 squared minus -1 squared. And that's going to be equal to 1/2 times by -1, so -1/2. Let's check it. So it was tangent of x, and then secant of x, that was squared, right? Oops. Tangent of x, secant squared dx, and that was from -π4, -π4, and that was to 0. And something's not working here. Okay, just need to add another parenthesis there. Get -1/2. There we go. Okay, last two. So here I do have a product, and I do see that the inside derivative, which would be -2x, which could cancel that x right there. So let's allow u to be equal to 1 minus x squared, and that would make du equal to -2x, du dx, sorry, and dx would be equal to du over -2x. And then let's replace our bounds. So if I plug in 1, so this will be the integral. Well, let's plug in 0 first. If I plug in 0, I get 1. And if I plug in 1, that's going to be 1 minus 1, which will be 0. So notice that these bounds, which are now in terms of u, I'm probably going to flip those and make that negative. I'll do that in the next step. But we have x, square root of u, and then du divided by -2x. So those are going to cancel. Okay, now I do have this -2 constant, so I can bring this out to be -2. But remember how I'm going to flip these right here? So that's going to make it negative, which will then just turn it all positive because of that right there. So this will just be 1/2 integral from 0 to 1 of u to the 1/2 power du. The antiderivative of u to the 1/2 is 2/3 u to the 3/2. From 0 to 1, so that would be 1/3 when I multiply these together, and then I'll do 1 to the 3/2 minus 0 to the 3/2, and then that's going to be equal to 1/3. Let's go ahead and give that a go. 0 to 1. 0 to 1, x first, x, and then square root, was it 1 minus x squared? And, yep, and we do get 1/3. Alright, for the last one, now this one's kind of a, I'm not canceling anything out like I have been in these previous ones, like there's nothing really to cancel out. This right here, so this is actually pretty easy antiderivative if you've done it enough. So I understand if you don't really know what to do here, you can just use u sub, and you can say that u is equal to 2x minus 3. That will change this to be 1 over u, and that's an easy antiderivative. Yeah. So you can go through the whole process of using this u substitution, but because I see that this is just like, this is same as 1 over x, but the function of x is 2x minus 3 rather than x, which just means that it has a simple chain rule of 2 that you'll have to account for when you use the antiderivative. But I know that the antiderivative here, and again, this is just through experience, is going to be the natural log of 2x minus 3 divided by 2. So why divided by 2? Because of the chain rule. Now you can't do this in anything else like this or like this. Yes, you can do this here. You can skip past the u sub. But because the chain rule is only a constant, then I only have to divide by that. You can't divide by functions to undo the chain rule, though. So in any case, and I can check this, so the derivative of the natural log, well, so I have the 1/2 because of this 2 in the denominator, that's a constant, and then the derivative of the natural log is 1 over 2x minus 3, and then I would times by the derivative of the inside, which would be 2, so then you can see that that would cancel with that, and look, I get exactly what I just had right there. So through experience, hopefully that makes a little bit more sense as we go. But we're evaluating this from 2 to 5. So I'm going to put that 1/2 out here, and then we'll do the natural log, and we can plug in 5. So if I plug in 5, that becomes 10 minus 3, which would be 7. Now, I don't need the absolute value signs after I plug it in, since 7's positive, so I don't need to worry about it there. And then I'll do minus the natural log, and if I plug in 2, that becomes 4 minus 3, which would be just 1, natural log of 1. And the natural log of 1 is 0, so this becomes 1/2 natural log of 7. And 0.5 natural log of 7 is equal to 0.973 when I round. And so let's check this in my calculator. So 1 divided by 2, x, 1 divided by 2x, was it plus 3? Nope, it was minus 3. And we evaluated that from, what was it, like 2 to 5? And we got 0.97, and we've got 0.97393. Yep, there you go. Okay, so I hope you guys like these. They're good practice for u sub and just general antiderivatives. Hope you guys are getting the hang of these. They are tedious, I agree, especially this whole part right here where you have to plug in, you do the f of b minus f of a. Definite integrals get boring, not gonna lie. The f of b minus f of a part, the simplifying, the finding the value, it just can't, it's not always fun. So, but just takes a lot of practice to get used to. So anyways, hope it helped.